Good morning, everyone. I welcome you all to this next lecture of Dynamics of Machine, and we'll continue our discussion over the governor. Right. So, governor, we have first studied about the basic introduction of governor, the functioning of the governor. Then we saw comparison between flywheel and governor. Then uh, some basic terms and definitions related to the governor. After that, we saw the operation of governor, okay, how it operates. Then we started with the first type of governor, that is watt governor. So in watt governor, we saw the expression for uh, how to derive the height of the governor with the help of drawing the line diagram, and based on it we solved some numericals. Now in today's class we are going to start with the Porter governor. Okay, so this Porter governor is nothing but it is a modification of watt governor. The only difference is there is a central load light in this. Okay, there is a central load which is acting in this, which is acting in this governor. Okay, and that central load is attached to the sleeve. Okay, as shown in this figure. So this is sleeve, and the load is attached to the sleeve, and along with sleeve it is also mounted over the spindle. Okay, so as the spindle rotates, this uh, as the sleeve moves down, the load also moves up and down. All right, the load moves up and down the central spindle. Now what is the work of that adding the central load? So this additional downward force increases the speed of revolution, okay, which is required to enable the balls to rise to any predetermined level. So uh, this because it is a load, so it will have a downward force. Okay, so this downward force increases the speed of revolution which is required to enable the balls to rise. So whenever there is change in external load on the engine, the uh, balls will try to rise, and this central load will help them. Okay, we'll see how. Now for the ease of understanding, we have drawn the line diagram of one half of this Porter governor. Okay, so this is what is shown over here. So let's understand this first. So this is point P. Okay, uh, this is arm A from P to B is upper arm, and there would be some tension in the arm. Okay, because this ball is having its own weight. All right. B is the ball, and D is this point where the sleeve is attached to the spindle. Sorry, this lower arm or the link is attached to the spindle. All right, and this is point D. Same point D over here. Okay, so this angle is alpha, this angle is alpha, and this angle is beta. These two angles are different because D and point P do not lie exactly on the spindle. All right. Then there is centrifugal force Fc acting outwards. Uh, the weight of the ball is W. Okay. The weight of the sleeve, since total weight of the sleeve is capital W, and we are considering only one half for our study. Therefore, the weight which is acting on point D is half of the weight of the this central load. So it is capital W by 2. Okay, and the tension T2 is in the lower lengths, and obviously this is the radius and this is the height of the governor. All right. Now, as done previously, we'll do the we'll write the balancing equation, force balancing equation. That is equilibrium equation. So small m is the mass of each ball in kg. The nomenclature which is given here is small m is the mass, okay, and small w is the weight of each ball in newtons, okay, and it will be calculated by m into g. All right. Capital M is the mass of central load, okay. The mass of central load is capital M, and its weight would be capital W, and it will be M multiplied by G, okay. Capital M multiplied by G. R is the radius of rotation in meters. Small h is the height of the governor. N is the speed of balls in RPM, and omega is angular speed. Fc is the centrifugal force acting on the ball. So this Fc, centrifugal force, which is acting outward. It is to be taken in newtons, and its value m omega square r. Okay, T1 and T2 are the forces in arm and leg, that is upper arm and lower arm, as shown over here. Okay, T1 and T2. Alpha is the angle of initiation of the arm or upper link to the vertical. So this is angle alpha, and it is the angle of inclination of this upper arm, and beta is the angle of inclination of the lower arm with the vertical axis. Okay, all right. So I hope the nomenclature and the diagram is clear to you. Let's forward. Now consider the equilibrium of forces acting at D. We are considering this point D. Okay, we are considering this point D. So what are the forces acting on point D? It is W by 2. Then there is this tension. Okay, so since this T2 load is at some angle, we have to resolve it horizontally and vertically. So this would be T2 cos beta, and this would be T2 sin beta. Okay, so since there is no horizontal force acting on it, so W by 2 would be equals to T2 sin beta cos beta. Okay, let's watch it. So as previously explained in the previous slide, that this T2 cos beta would be equals to W by 2. Okay, and W by 2 is W is capital M into G. So this T2 becomes mg upon 2 cos beta. Okay, so at point D, we have considered the equilibrium of forces and derived that T2 would be equals to capital Mg divided by 2 cos beta. Okay, now consider the equilibrium forces acting on B. Okay, the point B is in equilibrium under the following force, action of following forces: weight of ball, centrifugal force, tension, and so we'll go to previous slide again. This we are talking about this point B. So what are the forces that are acting on point B? One is this centrifugal force, which is acting horizontally. Another one is this weight of the self weight of the ball, okay, which is small w, and this small w would be m multiplied by g. Okay, another force which is acting is the T1 force. Okay, so this is T1 force and this is T2 force. So this T1 force, since this angle is alpha and this is 90 degree, this angle would be 90 minus alpha. Okay, similarly, this lower angle would be 90 minus beta. So the horizontal component and vertical components would be somewhat in this way. Okay, so for T1, this horizontal component, sorry, this vertical component, what will be the vertical component? Its vertical component would be T1 sin 90 minus alpha, right? 90 minus alpha. I am writing alpha as A. Okay, so 90 minus theta is cos theta, so it will become T1 cos A. Okay, it will become T1 cos A. And similarly, this uh, vertical component, what it would be? Vertical component would be T1 cos 90 minus alpha, right? T1 cos 90 minus alpha. T1 cos 90 minus alpha, and it will become equal to cos 90 minus theta is sin theta. So it will become T1 sin alpha. Okay, I hope this is clear to you. Similarly, we'll resolve this T2. So horizontal component of that would be T2 sin T2 cos 90 minus beta. So it will become T2 sin beta. Okay, and its vertical component would be T2 cos beta. Okay, all right. So that is what is written over here. First, we'll write the horizontal. Uh, First, we'll write the vertical, the forces which are acting vertically. So resolving the forces acting vertically. See, there are four forces. Small w, that is weight of the ball, centrifugal force, the tension in the arm T1 and the tension in the arm T2. So resolving forces vertically. The only force acting in the upward direction, is T1. This is cos 90 minus alpha. So the upward component of T1, right? So this T1 cos alpha would be equals to T2 cos beta plus W. Why? Because downward force, there are two downward force, that is this W and the cos component of this T2. Okay. So this T1 cos alpha is equals to T2 cos beta plus W, or T2 we know we can write it as mg 2 cos beta. Okay, so cos beta got cancelled plus mg, right? Again, now we'll resolve them horizontally. So in horizontal direction, there are again one force is the centrifugal force, and two forces would be components of horizontal components of T1 and T2. So T1 sin alpha plus T2 sin beta would be equals to Fc. We substitute the value of T2. Okay, so it comes out to be T1 sin alpha is equals to Fc minus mg by 2 into tan beta. Okay, now this is equation number 2, in which we wrote the value of T1. This is equation number 1. This is equation number 1. This is equation number 2, that T1 cos alpha is equals to capital mg by 2 plus mg. Okay, and we will divide it T1 sin alpha upon T1 cos alpha. From here, this is, I guess, equation number 3, that this is T1 sin alpha. Okay, this is equation number 3. So we will divide 3 by 2. Okay, because cos alpha is over here. So T1 sin alpha upon cos alpha, and once we simplify and solve it, we will reach that mg by 2 plus mg by 2 is equals to this value. Okay, and we'll substitute tan beta upon tan alpha is equals to q. Okay, because it is repeated again and again, and tan alpha is equals to r by h. How? Because in the diagram we can see in this triangle, tan alpha would be perpendicular upon hypotenuse, so it will be r upon h. All right. So mg by 2 plus mg is equals to m omega square r. This fc is m omega square r into h by r. Okay, because this was tan alpha, so it will become h by r minus mg by 2 into q. So this tan beta upon tan alpha is equals to q. Okay, or m omega square r h, m omega square h is equals to mg plus mg by 2 into 1 plus q. Okay, now we want to determine the height. So this height comes out to be h is equals to m plus capital M by 2 into 1 by q upon m into g by omega square. Okay, and omega square can be determined as this value. So omega square is m plus capital M by 2 into 1 plus q upon m into g by h, or it can also be written in terms of n square, that is n square is equals to m plus capital M by 2 into 1 by q upon m into 895 by h. Okay, so as you can see that in case of Watt governor, this n square was 895 upon h. Okay, 890 upon 85 upon h in case of Watt governor. Here you have this extra term m plus capital M by 2 into 1 plus q divided by. Okay, so this is extra. So this is the expression which we are going to use for determining the various values. All right, this equation number 5. Okay, so also we need to remember that this tan beta upon tan alpha is equals to q and tan alpha is equals to r by h. Okay, now few things to keep in mind. And tan alpha is equals to tan beta. Okay, that is when inclination, when the lengths are equal and this P and D point lie at the same line. Okay, when this upper arm and lower arm are equal and this both are lying on the same vertical line. Okay, in that case the angle alpha and angle beta will be equal, and hence tan beta is equals to tan alpha, so q will be equals to 1. Okay, this q will become equal to 1, so 1 plus 1 will be 2 and 2 will cancel the 2, so this equation will become n square is equals to m plus capital M by small m into 895 by h. Okay, so if it is given that both angle are equal, then we can use this equation for determining the value of n. When the loaded sleeve moves up and down the spindle, the frictional force acts on it in a opposite direction to that of motion of sleeve, right? So since there is load, there will be some friction also. So if the friction is given to us, what we have to do is here we have to add or subtract the friction. Okay. So in this equation, it will become n square is equals mg plus capital mg plus minus by 2 into 1 plus q upon mg into 895 by. Okay, so when we simplify it, it will become something like this when q is equals to 1. The plus sign is used when the sleeve moves upward, governor speed increases. Okay, if the this is moving upwards, sleeve is moving upwards, then the friction force will be acting downward and it will be in the direction of weight itself. So we'll use with plus sign, and vice versa when the governor when the sleeve is moving downwards. Okay, all right. So this was the derivation with the help of equilibrium, writing the equilibrium equations of different points. Now another method is the this instantaneous center method. We'll take moment about I13 again. How these points came is with the help of by drawing the instantaneous centers. Okay, so this is the diagram, and this is the sleeve, and weight is mounted over the sleeve. Okay, therefore it's the force which is coming on the sleeve is capital Mg plus minus F divided by 2. Again, we are considering 1/2 of this for the ease of explanation. Okay, where M is the mass of sleeve or mass on sleeve, and F is the frictional force. All right. Again, I have taken this angle as theta. Previously, it was alpha, and this angle is beta only. This upper arm is mounted at point N. The ball is at point B, and lower arm is mounted to the sleeve at point R. Okay, and instantaneous center is I13. It is at Q. Okay. All right. The centrifugal force acting on the ball is mr omega square. It is horizontally outwards. Small mg is horizontally, it is vertically downwards. Since this angle is theta, this angle also would be theta. Tan theta would be r upon h. Okay, and here tan theta would be c by a. So this distance e, this vertical distance is a, and this distance SR is B. Over here, tan beta is equals to B upon A. Okay. With the help of geometry, we can determine this. Now, when we take the moment about I13, so taking moment about I13, what we'll obtain is the forces m omega square r. Where is m omega square r? It is over here. So its line of action is passing over here, and the perpendicular distance of this point from this line of action is A, is equals to A, this distance. Okay. So this will tend to rotate it in anti-clockwise direction, and other forces, which is mg, this mg force, the line of action of mg force is like this, and the perpendicular direction from this point is C. Okay, this will tend to rotate the system in clockwise direction, and another force, that is mg plus minus F by 2. This is also acting downwards, and its distance from Q is B plus C. Okay, so this is what is written over here. There is only one force which tends to rotate the system in anti-clockwise direction, and the two forces which will tend to rotate the system in clockwise direction. Okay, so they have been taken with the appropriate signs. So we came to this equation that mr omega square multiplied by A would be equals to mg, small mg, this multiplied by C, plus this force mg plus minus F by 2 multiplied by C plus B. Okay, so this is the governing equation, or this is the moment balance equation, right? So what we'll do is we'll try to make this tan theta by dividing it by A, because in through geometry we can see that C by A is equals to tan theta, C by B is equals to tan, B by A is equals to tan beta. So we have done that. Then tan theta is taken common. Okay, so here it becomes tan beta by tan theta. So tan beta by tan theta is equated as K. Okay, and tan theta is R by H from this triangle, right? From triangle OPN, tan theta is R by H. So R and R gets cancelled, and tan beta by tan theta is equals to K. So what we have taken as Q over there, this I have named as K. All right. So it is from. So this omega square becomes from here, it will become m omega square is equals to 1 by H small mg plus capital Mg plus minus F by 2 into 1 plus K. Okay. So this becomes omega square is equals to 1 by mg small mg plus capital Mg plus minus F by 2 into 1 plus K. and if we want the expression for height, then we'll cross multiply it. So h becomes 1 upon m omega square mg plus minus plus capital Mg plus minus f by 2 into 1 plus 2. Okay, so it might look a bit big equation, but it is the generalized equation. Okay, now assume if the arms are of equal length and pivoted at same distance from the axis, that is uh, these two arms, the upper arm and the lower arm. Upper arm and lower arm are equal in length and they are mounted at the same uh, vertical axis, because here they are mounted on different vertical axis. Okay, therefore these two angles are different, theta and beta. Now consider they are mounted on same vertical axis and the lengths are also same, then alpha and beta will be equal. If alpha and beta theta and beta would be equals. If theta and beta are equal, then this k will become 1. If the k become 1, this equation becomes 1 plus 1 is equals to 2, and 2 and 2 would get cancelled. Okay, and also if the friction is negligible, if it is well lubricated and the value of friction is very less, then this f will become 0. So this equation comes out to be h is equals to 1 by m omega square into mg plus capital Mg by 2. This 2 and 2 will get cancelled. So we'll arrive to the equation 1 upon m omega square, or g will be taken common. So h is equals to g by omega square m plus capital M by m. Okay. So also it can be if we take the omega over here and convert it into n, so we'll arrive to this equation again, that n square is equals to m plus m divided by small m into 895 upon h. Okay. So if the only difference from, again I'll point it out, the only from Watt governor is, in Watt governor this n square, the value of this n square was 895 upon h. Okay. Since the friction force is equal to 0, so now it can be compared to the Watt governor. So only difference is this factor m plus capital M divided by m. Okay. Now in case of Watt governor, the height of governor is independent of mass of balls, while in Porter governor, uh, Porter governor has relation between height of governor and mass of balls. So as in the Watt governor, there was, this term was not there, right? So the height was not related to the mass of the balls. But in case of Porter governor, the height is somehow related to this mass of the balls and also the mass of the sleeve. All right. Now, thing in case of Watt governor, the difference in sleeve positions at higher speed is marginal. Whenever the engine is running at high speed, let's say at 100 rpm, and there is a change from 100 rpm to 110 rpm. So the change in the height of the governor was very small. Okay, so at high speeds, it became less sensitive. This is what this sentence says. That at high speed, the change was very marginal. The change and the difference in the sleeve position at higher speeds was very marginal. Okay, but in Porter governor, the difference between the sleeve positions at higher speed is magnified by the factor m plus capital M by small m. Okay, so it will be sensing the change in speed in a better way. Okay, at higher speeds, and the range of the governor, it can be calculated with this formula, that is n max minus n min. Okay, so again, just to summarize the formulas, if the value of friction force and the value of theta and beta both are given to us, then we can use any of these expressions, okay, to determine the omega or to determine h. It is nothing but we have just cross multiplied the values. And in case of n square, if you want to calculate in terms of n, then it would be something like this. Okay, and if this, so these are the generalized equations. If friction is not given to us, we'll ignore this value. If theta and beta are equal, then we'll use this formula. Okay, because once you substitute the value of k is equals to 1, this 2 and 2 will get cancelled, and you will get m plus capital M by this small m. Okay, so I hope this is clear to you. Now let's go through some numericals. So a Porter governor has equal arms, each 250 mm long. Okay, equal arms are given to us and pivoted on the axis of rotation. So both the arms are pivoted on the axis of rotation. From this, we can determine that alpha and beta, or theta and beta, both are equal. Each ball has a mass of 5 kg, small m is given, and the mass of central load on the sleeve is 25 kg. Okay, so capital M is given to us as 25. The radius of rotation of ball is 150 mm. Small r is given. When the governor begins to lift at and 200 mm, when the governor is at maximum speed. So two heights are given to us. Sorry, radius of rotation is r, and when the governor begins to lift and 200 mm, when the governor is at maximum speed, the height at max speed is given to us, right? Find the minimum and maximum speed and range of the speed of governor. So we have to determine nmax, nmin, and its range. So we have to draw this diagram, right? Uh, when the this radius is 150 and the when this radius is 200 mm. Okay, so two radiuses are given to us, and accordingly we have to we can determine the height. Okay, so this is the minimum position and this is the maximum position. When the uh, height reduces, the speed increases, right? So we have to determine the omega or n for this case, and again n for this case. So friction is not given to us, and also these angles, since they are inclined at same vertical axis and these lengths are equal, therefore both the angles theta and beta would be equal, right? So it is shown in the figure A and B, minimum and maximum position. Now let's start solving. When the speed, no, when the minimum speed, that r1 is equal to 0.15 meter. Okay, n1 is the minimum speed. So h1 would be equals to this, h1 would be equals to this pg, and it will be equals to under root of 250 square minus 150 square. So it comes out to be 0.2 meters. So we have the value of h, we can calculate the value of n. So n is equals to m plus m by m into 895 upon h. So it would be 5 plus 15 upon 5 into 895 by this. Okay, they have not calculated and they have not multiplied by g, because g and g will get cancelled. So n1 comes out to be 133.8 rpm. Okay, so this is the minimum speed. Now similarly we can calculate the maximum speed, because the geometry these values are known to us. So n2 comes out to be 154.5 rpm. Okay, and we know that the range can be calculated maximum minus minimum, so it comes out to be 20.7 rpm. Okay, so this is how we need to approach the numerical in case of watt governor. I hope this is clear to you. We'll conclude our class here. We'll continue in the next class. Thank you.